All right. We are late. We are late, you guys. I'm sorry. I'm sorry. We're late. Hello, everybody. Welcome back to the stream. I hope you're having a wonderful day so far. Apologies for running behind. I just one of those days, just tired and work and just was long and it's hard, guys. It's hard sometimes. Hey, Tim. Mahan, Wing On, my boys, my bros, welcome back. Hey guys, how you guys doing? The three amigos. All right, today we got some. Stop by the Dollar Tree, Le Dollar Tree. Stop by Le Dollar Tree. Got some Hershey's Kisses. That's what we'll be snacking on tonight. Yeah, we switched up the title tonight. We'll see if YouTube will YouTube will pick us back up here. You should see my analytics chart. It looks like the stock market. Edwards, welcome back. Oh, chapter 3 title says 2. My fault. Good catch, Mahan. Good catch. Let me fix that. You are correct. What is that up there? All right, chapter 3. All right, here we go. And chat too. Man, you can tell I'm not on the ball today, guys. Man, dude, I am just not on my A game here. Another day. Yesterday I couldn't read, and today I can't think, so it's just getting worse. Maybe I have a problem. I was struggling through the reading yesterday, dude. I was stuttering left and right. It was so bad. All right, we're loaded up. Marty, welcome, Marty. I appreciate you coming in. Yeah, we've been stuck on 1.6 for a minute, Tim. Exactly. I think YouTube's been they've been on me, and so like I said, is I turned off the well, it all started when I turned off the super chats. So I turned it off because YouTube was taking like a 40% cut, 50% cut out of your guys' super chat. So I was like, no way am I going to let them just rip you guys off like that. So I took it off, and they're making me pay the price. All right. Let's go ahead and get into this. Okay, we can't be eating chocolate if we're going to be reading. That's just not going to work. Chocolate and Coke. Probably not a good combo for the dentist. Oh, Tim wants to do Elite Code tonight. We'll do Elite Code tonight. We'll do the next one. I don't think this chapter's as long. Okay, guys, let's get into this. We are in chapter 3 already of Git. There's 10 chapters, so we're already almost halfway there. We'll be really pushing forward towards the end of the book in just a few short, like in a week's time from right here today. After today, a week from today, we'll be done with the book, and we'll pretty much have all of the knowledge that we'll need to move forward with our careers in programming using Git. And obviously, there's still more to learn, but we'll have a great tool set given to us here and provided through this book to be able to kind of manage our projects on GitHub and also manage like pull requests and things like that. Make sure that everything works out and be kind of, if we're going to kind of own projects and be the owner of projects, we're going to need to know how to, manage all this stuff with everybody. Yeah, Tim. No, I agree with you there. Like a Well, it wasn't just YouTube. So YouTube took like a 30% hit, and then the App Store, like if it was through like the App Store, Apple took like another 30% hit. So I got like 40% of the dono, and I'm not even concerned about that part. I'm mainly concerned at this like the ethical concerns of taking 60% of someone's donation is kind of I personally would not want to donate and to I'm not donating to the company, I'm donating to the person. So I disagreed with that, so that's why I turned it off. All right, Wing Hong, I'll do the reading for us. Let's you just sit back and relax. Let's get into Git chapter 3, Git Pro Git. So I did go ahead and push this to a repo on GitHub. You can go ahead and access that in the link down below. You can also join my Discord link down below and get access to all of my study resources in a kind of general roadmap on the server. Thanks so much for being here, everybody. Let's go ahead and dive on into 3. Nearly every version control system has some form of branching support. Branching means you diverge from the main line of development. Okay, so branching means that you diverge from the main line of development and continue to do work without messing with that main line. In many version control tools, this is a somewhat expensive process, often requiring you to create a new copy of your source code directly, which can take a long time for large projects. Some people refer to Git branching model as its killer feature. It has certainly set Git apart in the version control system community. Why it's so special? The way Git branches is incredibly lightweight, making branching operations nearly instantaneous and switching back and forth between branches generally just as fast. Unlike many other version control systems, Git encourages workflows that branch and merge often, even multiple times in a day. Understanding and mastering this feature gives you a powerful and unique tool, and you can entirely change the way that you develop. Branches in a nutshell. To really understand the way Git does branching, we need to take a step back and examine how Git stores its data. As you remember from what is Git, Git doesn't store data as a series of changes or differences, but instead as a series of snapshots, right? When you make a commit, Git stores a commit object that contains a pointer to the snapshot of the content you staged. This object also contains the author's name and email address, the message that you typed, and pointers to the commit or commits that directly came before this commit. So it's like a linked list almost, right? It's parent or parents. 0 parents for the initial commit, 1 parent for a normal commit, and multiple parents for commit that results from a merge of 2 or more branches. To visualize this, let's assume that you have a directory containing 3 files, and you stage them all and commit. Staging the files computes a checksum for each one. The SHA1 hash we mentioned in what is Git stores the version of the file in the Git repository. Git refers to them as blobs. Okay, so blobs, right? See, these are files stored in the Git repository. Git repo. Git repository. That has files that have been checksummed hashed stored in the Git repository. And stored in the Git repository. So much tracked. I was just here the other day and you were looking at Git, LOL, grinding Git. Hey, thanks for coming in, dude. Appreciate you for joining me. My name's Michael for everybody here. I appreciate you guys joining. We're reading Pro Git. I have a link down below for my Discord if you want to get access to all my resources for this book so far. We're on chapter 3. We're doing a chapter a day. It's only 10 chapters, so we'll be done within a week's time from now. So really awesome. I have a degree in human biology and a minor in chemistry, and I graduated back in 2021. I've been teaching myself how to code for about 10 months, and it's been really fun. I've been building projects, streaming my entire progress live every single day after my 9 to 5 job. So thank you guys so much for being here. Consider following along if you're new, and throw a thumbs up if you're part of the early crew here. It really helps the stream. Now let's go ahead and keep moving. Okay, blobs. And so let's assume that you have a directory containing the files. You stage all of them, commit. Staging the files computes a checksum for each, stores that version of the file in the Git repository, refers to them and adds the checksums to the staging area. When you create the commit by running git commit, git checksum each subdirectory, in this case just the root project directory, and stores them as a tree object in the Git repository. Git then creates a commit object that has the metadata and a pointer to the root project tree so it can recreate the snapshot when needed. Your Git repository now contains 5 objects, 3 blobs, each representing the contents of one of the 3 files, 1 tree that lists the contents of the directory and specifies the file name, which files names are stored as which blobs, and 1 commit with the pointer to that root tree, and all the committed metadata. Okay, so these are the blobs for the 3 files, which are inside the tree object. Right, this is blob 1, blob 2, and blob 3 for the 3 files. Then you have commit, so it's the 3 things, 5 things, 5 objects, 3 blobs, 1 tree, and 1 commit with the pointer to the root tree. Okay, so a commit and a tree. If you make some changes and commit again, the next commit stores a pointer to the commit that came immediately before it. So here, the initial commit of the project in snapshot A is all this, right? In snapshot B, we fixed a bug and references a parent and a parent, which is this and that. Okay, cool. A branch in Git is simply a lightweight movable pointer to one of these commits. The default branch name in Git is master. Okay, so we'll say default name in Git is master. As you start making commits, you are given a master branch that points to the last commit you made. Every time you commit, the master branch pointer moves forward automatically. So snapshot A was our first iteration, our initial commit. We then linked that to snapshot B, which links to snapshot C, which trace all the way back to the beginning of our project. And at this point in time, our master branch is currently on our commit from snapshot C. And we have a tag here, version 1.0. Creating a new branch. What happens when you create a new branch? Well, doing so creates a new pointer for you to move around. Let's say you want to create a new branch called testing. You do this with the git branch command. This creates a new pointer to the same commit you're currently working on. So 2 branches pointing into the same series of commits. So for this commit here, under this hash code, we have the master branch, and then we have a testing branch on the same commit. Okay, so you just branch off at this snapshot, and you can start working on this snapshot in a different, and then if it works, you can merge the snapshot in to the master branch. Okay, I get it. I'll be your audiobook, so much tracked. I'm reading out loud here. Do you sometimes forget to process what you're reading, or is it just me? Yeah, definitely. I think that happens to everybody. I have to go back sometimes, and it gets better. It gets a lot easier, though. That feeling comes around less and less, that like mind wandering, as you practice reading, right? So I don't know, it's kind of silly to think about practicing reading, but it's really true. It's kind of like with anything is at the start when I was first reading DSA and Python or Python Crash Course, I find myself wandering off like once every page. But now, it happens a lot less just because I'm more focused, and I think also I removed short form content from my life. So I got rid of, hey, Glump, we got a raid with a party of 6 on Twitch. Hello, everybody. Thanks for coming in. I appreciate you joining me. My name's Michael. I have a degree in human biology and a minor in chemistry, and I work as a formulation chemist for a biotech company. I'm just teaching myself how to code after my job, where I make projects, read books, and do courses, and just learn more stuff. So thanks so much for being here. Appreciate you coming in. Thanks, Glump. You're awesome, man. Um, That's awesome. I'll be finishing up a bachelor's for CS soon. Sucks that university cares more about human interaction and math courses over what's being paid for. I have to teach myself just to get ahead. Yeah, that's what a lot of people have been saying, that they're having to do a lot of extra work individually learning topics to be prepared for the field. Do you find that that's true in your case? It's interesting coming from a biotech uh, degree. Okay, so we're on chapter 3 here of Git. We're continuing on. How does Git know what branch you're currently on? Okay, it keeps a special pointer called head. Note that this is a lot different than the concept of head in any other VCSs you may be used to, such as Subversion or CVS. In Git, this is a pointer to the local branch you're currently working on. And in this case, you're still on master. The git branch command only created a new branch. It did not switch to that branch. Okay, so we'll say creating branches. And we'll go like this and give command here. It says, we're going to say head is a pointer to the current working branch, right? To the current working branch. Hey, how's it going? No, I appreciate you coming in. Game in Yoon and THI, do you have something? 1702. I call you Mr. 1702. Thanks for coming in. I appreciate you being here. Greetings. No, I don't. You're fine. I love chatting with you guys while I'm reading along here. It's all good. All right. Did you learn? Did you begin learning when you began making videos? Yeah, pretty much. I started a little bit before I started the channel with Harvard CS50P. That's what I kind of like dipped my foot in the water with, in terms of seeing if this was something I wanted to spend more time in. I really enjoyed the course and especially the project. Afterwards, making my own project really sparked this fire. And after I completed the project, that's when I made like these kind of first form videos and started reading Python Crash Course and stuff like that. So um, I yeah, that's what it's been. So thanks so much for being here. Yeah, I'm going for specialization in cybersecurity programming and haven't have done any and haven't have. I'm guessing you meant to say haven't done any programming. Makes no sense, but I'll have a piece of paper to show I attended. Oh, you said haven't. Gotcha. Well, yeah, that's rough, man. It's so weird, right? Cybersecurity programming with no programming. It's so conceptual. It's crazy. Okay, head is a pointer to the current working branch. Creating a new branch does not move the head pointer from right. Must move manually. What happens with testing, right? Call the head. Now this is a lot different than the head. You're still working on master. The git branch only created a new branch. It did not switch to that branch. You can easily see this by running git log command that shows you where the branch pointers are pointing. This option is called -- decorate. Okay, so we'll say, right, you can do git branch name. And then we'll say new branch name, right? and then it goes, so you can, that's how you create a new branch from the current working branch slash, right? Ultra Instinct 121. How long did it take you to get fully comfortable with OOP? Well, I still got a lot to learn myself, but in general, I do have a fairly maybe kind of dipping into intermediate level of object-oriented programming, especially in Python with special methods. I've really come to learn quite a few of them now with the data structures and algorithms in Python book that we've been reading, as well as Fluent Python that we've been reading. It really goes into those special dunder methods within there. But all of my projects I made so far have been completely object oriented. So, I guess that kind of answers it. Like if I show you guys here, for those that are new to the channel, this is the current project we're working on live that I've written entirely from scratch in Python using Tkinter. It's a small business manager where the user will be able to load in and populate inventory items. They have their entries checked via certain functions. They can search and populate this matrix for specific search parameters and searching for various items or selections of items. They can refresh the matrix back to the default state. Same thing for expenses, where they can add in expenses with various information, search for those expenses via these column headers, and then refresh the matrix from there. And then they can transact available inventory items and also return not unavailable inventory items or sold inventory items. So you have the ability to sell and return those. And all this is happening on the back end with a SQL database, SQLite, and right, and so those are being logged here. As you can see, item number 1 was sold, returned, and then was sold again. So as you guys can see and then what it does is that your transactions for those calendar years automatically generate and populate income statements for this business user. So if you guys are familiar with any counting principles, you have income statements. So as you can see for 2025, we made 1, 2, 3 sales totaling $75, and we made 1 return totaling 30. So you can see the gross sales is $75 with a $30 in allowances. So, and then sales transport is all of these fees, shipping charges added up and whatnot for these transactions. So that's where that's all coming from. And next thing you know, you get a nice net income at the end of it. So it automatically does this for the user. So we are going to work on the balance sheet hopefully later tonight is my goal, but we might not get to it because we started late today, unfortunately. I keep procrastinating finishing this project, but we're almost done. We're almost done. We're like 90%. And then this is our CS50X final project. All right. Let's keep on moving on the book. Gosh, we got to keep moving. I keep stalling. Thanks, Game and Yoon, for coming in. Appreciate you. You're awesome. Thanks for coming in. So you can call the decorate to see where the branches are pointing. So you can say git log dash dash decorate, right, will show the head pointer location. Oh, Soma, there's a lot of people in the Discord that are really good at C++. You should definitely join the Discord and chat with them. There's a couple people making some games and stuff, so it's pretty cool. Okay, so use the decorate. You can see that the master and testing branches that are right there next to the F30, right? To switch to the existing branch, run git checkout command. This lets you let's switch to the oh my gosh, let's switch to the new testing branch, git checkout testing. Okay, so we'll say git checkout branch name, right? This will switch the head pointer to the indicated branch. Okay. Checkout testing. This moves head to the point to the testing branch. Perfect. What is the significance of that? So let's do another commit. Vim test.rb git commit dash a dash m make a change. So it moves a change on to testing here. The head branch moves forward with the commit is made. This is interesting because now our testing branch has moved forward, but your master branch still points to the commit you were on when you ran git checkout to switch branches back here. Let's switch back to the master branch. So git checkout master. Note, git log does not show all the branches all the time. If you were to run git log right now, you might wonder where the testing branch is you just created. Where it went, as it would not appear in the output. The branch just hasn't disappeared. Git just doesn't know that you're interested in that branch, and it's only trying to show you what it thinks you're interested in. In other words, by default, git log will only show commit history below the branch you've currently checked out. Okay, because the testing branch is currently above it in the series of commits, the master branch won't show it on the git log. Thanks for coming in, Ultra Instinct. Yeah, I've come a long way in these 10 months, but we got a long ways to go here. We've been doing everyday work, so it's paying off here. The command did two things. It moved head pointer back to point at the master branch, and it reverted the files in your working directory back to the snapshot that master points to. This also means that the changes you made from this point forward will diverge from an older version of the project. It essentially rewinds the work you've done in your testing branch so you can go in a different direction. Let's make a few changes and commit again. Vim test.rb git commit append or -a-m make other changes. Now in your project, what does the -a do in the commit? Do you guys remember from chapter 2? Git log, git commit, makes git automatically stage every file that's already tracked, skipping the git add part. Okay. Cool. Now your project history has diverged. See divergent history. You created and switched to a branch, did some work on it, and then switched back to your main branch and did other work. Both of those changes are isolated in separate branches. You can switch back and forth between the branches and merge them together when you're ready. And you did all that with a simple branch, checkout, and commit commands. Right, so we did work on master, and we did individual work on testing and committed those individually. So now we've branched off from our main chain. Okay. You can also see this easily with the git log command. If you run git log one line decorate graph all, it will print out all the history of your commits, showing you where the branch pointers are and how your history has diverged. Let me bring this up so it's not cut off for you guys. So git log one line decorate graph all gives you the hash code. Head masters the current head pointer on. This was the previous commit that you're working on. Within here you have testing though, that's in another branch that's being branched off. Okay, so it's showing you this other branch here off of the main branch here. Interesting how they display this with ASCII. Because a branch in Git is actually a simple file that contains 40 character SHA1 checksum of the commit it points to. Branches are cheap to create and destroy. Creating a new branch is as quick and simple as writing 41 bytes to a file, 40 characters, and a new line. This is in sharp contrast to the way most older VCS tools branch, which involves copying all of the project files into a secondary directory. This can take several seconds or even minutes depending on the size of the project, whereas Git in the process is always instantaneous. Also, because we're recording the parents when we commit, finding a proper merge base for merging is automatically done for us and is generally very easy to do so. These features help encourage developers to create and use branches often. Let's see why you should do so. Note, creating a new branch and switching to it at the same time. It is typical to create a new branch and want to switch to that branch at the same time. This can be done in one operation with the git checkout -b new branch name. Okay, so we'll go like this. Right, this will create a new branch and auto switch the head pointer to it. From Git version 2.23 onwards, you can use git switch instead of git checkout. 2. Switch to an existing branch. Switch between testing, git switch testing branch. Create a new branch and switch to it. Git switch -c new branch. The -c flag stands for create. You can also use the full -- create. Return to your previously checked out branch with git switch --. Interesting. So we'll say git switch can be used instead of git checkout. Okay, and we say to switch to an existing branch. This will switch to an existing branch. Create a new branch and switch to it. So here, create a new branch and switch to it. Which the head pointer to it. The flag -c stands for create. Can also use -- create. And then lastly, git switch -- right, this will return your previously checked out branch. Return to your previously checked out branch. Next. All right, 3.2. Moving on, boys. Let's go. Git branching. Basics. Basic branching and merging. Is this one long? Oh, it looks a little long. Okay, it's fine. Let's basic branching and merging. Okay, let's go through some simple examples of branching and merging with a workflow that you might use in the real world. You'll follow these steps. Do some work on a website. Create a branch for a new user story you're working on. Do some work on that branch. At this stage, you'll receive a call that another issue is critical and you need a hot fix. You'll do the following. At this stage, you'll receive a call that another issue is critical and you need to hot fix. You'll do the following. Switch to your production branch. Create a branch to add the hot fix. After it's tested, merge the hot fix branch and push to production. Switch back to your original user story and continue working. Interesting. Branching, basic branching. First, let's say you're working on your project and have a couple of commits already on the master branch. Okay. You've decided that you're going to work on issue number 53, if whatever issue tracking system your company uses. To create a new branch and switch to it at the same time, you can run the git checkout command with the -b branch, -b key switch. Git checkout -b, that commit. Switch to a new branch, issue 53. This is short for git branch, git checkout. So we can git checkout branch this one. Okay, so now we have we have created a branch and checked out that branch at this C2 commit for issue 53. We're going to fix a bug on this C2 commit. Creating a new branch pointer. You're working on the website and do some commits. Now, doing so moves the issue 53 branch forward because you have it checked out. That is your head is pointing to. Right, so we've done a commit here of commit number 3 on issue 53 because we had checked out, and which moved our head to the issue 53. The issue 53 branch has moved forward with your work. Now you get the call that there is an issue with the website and you need to fix it immediately. With Git, you don't have to deploy your fix along with the issue 53 changes you've made, and you don't have to put a lot of effort into reverting those changes before you can work on applying your fix to what is in production. All you have to do is switch back to your master branch. However, before doing that, note that if your working directory or staging area has an uncommitted change that conflict with the branch you're checking out, Git won't let you switch branches. It's best to have a clean working slate when you switch branches. There are ways to get around this, namely stashing and commit amending, that we'll cover later on, in stashing and cleaning. For now, let's assume you've committed all your changes, so you can switch back to your master branch. Git checkout master, switch back to branch master. At this point, your project working directory is exactly the way it was before you started working on issue number 53, and you can concentrate on your hot fix. This is an important point to remember. When you switch branches, Git resets your working directory to look like it did the last time you committed that branch. It adds, removes, and modifies files automatically to make sure your working copy is what the branch looked like in your last commit. Next, you have a hotfix to make. Let's create hotfix branch on what we're working on, which to work until it's completed. So we had that C3 that was branched from C2 for issue 53. We committed back, we checked out back into master, and now we're having a hotfix onto master. So we're probably going to merge both of these into master, is my guess. So we check out and create a branch for hotfix, as it's the branch name. We switch to that, which switches to the new branch. We do some work on it. We commit broken email address, fix broken email address, and that's the hotfix commit right there. Okay. You can run your test, make sure the hotfix is what you want, and finally merge the hotfix branch back into your master branch to deploy to production. You do this with the git merge command. You'll notice the phrase fast forward in that merge because the commit C4 pointed to by the branch hotfix you merge in was directly ahead of the commit C2 you're working on. You notice the phrase fast forward in that merge. Oh, hold on. So you can run your test, make sure the hotfix is what you want. You can finally merge the hotfix branch back into the master branch. Okay, exactly. So we're going to merge this hotfix back into master. You'll notice the phrase fast forward in that merge because commit C4 points to the hotfix branch. You merged it when directly ahead of the commit C2 you're on in the master. Git simply moves the pointer forward. To phrase that another way, when you try to merge one commit within a commit that can be reached by following the first commit's history, Git simply simplifies things by moving the pointer forward because there is no divergent work to merge together. This is called fast forward. Okay, because that's what, so think about this. It's if you create a branch off of the master branch and then merge the master branch in that newly created branch together, well, your master branch just becomes this hotfix branch because it just creates a new pointer to that, because all you did was make a copy of master, do some more work on top of it, and then merge it together. Well, your pointer just is now going to point to C4 right here and master. Perfect, exactly. Um, gotcha. So I'll go here, I'll say fast forward. Right, that is when merging a branch, that is explain fast forward in Git in easy terms. I think give Git like a timeline of your project, fast forward and Git. And it's like this: you're on checkpoint A, you did something else, make more checkpoints in the straight line. B, C, D. You haven't made any new checkpoints on your own, so the timeline just moves forward to catch up. When you do a merge, Git sees there's nothing to merge, just new commits ahead, so it's simply fast forward. Okay. When merging a branch that is in direct line with the receiving, whatever. I'm not exactly sure how to phrase this. Anybody have a good definition for fast forward in Git? Not telling what you should do, but have you looked at Scrimba? No, I've never heard of Scrimba. What is that? After your super important fix is deployed, you are ready to switch back to work on what you were doing before you were interrupted. However, you'll first delete the hotfix branch because you'll no longer need it. The master branch points at the same place, so you can delete the with the dash delete option in Git branch. So this is Git branch delete branch name. Well, the flag indicates a deletion of the given indicated. Okay. Now you can switch back to your work in progress branch on issue 53 and continue working on it. So master is here, issue 53 is over here, and continue working. It's worth noting here that the work you did on your hotfix branch is not contained in the files in your issue 53 branch. If you need to pull it and merge it, you can merge your master branch into your issue 53 branch by running the git merge master, or you can wait to integrate those changes until you decide to pull the issue 53 branch back into master later. Basic merging. So you can, if you want, you can merge master into this branch if to get those changes from hotfix. If you want. Suppose that you've decided that your issue 53 work is complete and you're ready to merge them into your master branch. In order to do that, you'll merge your issue 53 branch into master, much like you did merge your hotfix branch earlier. All you'll have to do is check out the branch you wish to merge into and then run git merge command. So check out master, switch to master branch, merge issue 53 into master, merge made by the recursive strategy, index. Okay, perfect. This may look a bit different than the hotfix merge you did earlier. In this case, your development history has merged from some older point. Because the commit from the branch you're on isn't a direct ancestor of the branch you're merging in. Git has to do some work. In this case, Git does a simple three-way merge using two snapshots pointed to by the branch tips and the common ancestors of the two. So it looks here for the common ancestor. Okay, all the stuff that was different, all the stuff that was different merge onto the common ancestor. Instead of just moving the branch pointer forward, Git creates a new snapshot. One second, guys. I'm gonna run to the restroom. Give me 1 second. I appreciate you guys joining me here. I'll be back in 5 minutes. All right. I'm back. Hello. Thank you guys for waiting. I appreciate you guys being patient. Thank you guys so much for waiting for me. I'm back. Let's get this show on the road. All right. Welcome, everybody. Welcome back to the session here. Hopefully you guys that was a 5-minute little intermission. Hopefully you guys took a little break, got some water or something, and we're going to get back into chapter 3 on Git branching here. Okay. So we're trying to merge this. Looks a bit different than the hotfix merge you did earlier. In this case, your development history has diverged from some older point because the commit on the branch you're on isn't a direct ancestor of the branch you're merging in. Git has to do some work. In this case, Git does a simple 3-way merge using the 2 snapshots pointed to by the branch tips and the common ancestors of the 2. Instead of just moving the branch pointer forward, Git creates a new snapshot that results from the 3-way merge and automatically creates a new commit that points to it. Okay, a new commit here, commit 6. This is referred to as a merge commit and is special in that it has more than one parent. Now that your work is merged in, you have no further need for the issue 53 branch, so you can close the issue in your issue tracking system and delete the branch. Occasionally, this process doesn't go smoothly. If you change the same part of your same file differently in 2 branches you're merging, Git won't be able to merge them cleanly. If your fix for issue 53 is modified the same part of the file as a hotfix branch, you'll get a merge conflict that looks something like this. Git hasn't automatically created a new merge conflict or a new merge commit. It has paused the process while you resolve the conflict. If you want to see which files are unmerged at any point after merge conflict, you run git status. Git status on master branch, you have unmerged paths. Unmerged paths, both my index, HTML. Anything that has merge conflicts and hasn't been resolved and is listed as unmerged. Git adds standard conflict resolution markers to the files that have conflicts, so you can open them manually and resolve these conflicts. Your file contains a section that looks like this. This means the version in head, your master branch, because that was what you had checked out when you ran your merge command, is the top part of that block. Everything above the equal sign, while the version in your issue 53 branch looks like everything in the bottom part. In order to resolve the conflict, you have to either choose one side or the other or merge the contents yourself. For instance, you might resolve the conflict by replacing the entire block with "Please contact us at this." This resolution has a little of each section, and these lines have been completely removed after you resolved each of these sections in each conflicted file. Run git add on each file to mark it as resolved. Staging the files marks it as resolved in Git. If you want to use a graphical tool to resolve these issues, you can run git merge tool, which fires up an appropriate visual merge tool and walks you through the conflicts. This message is displayed merge because merge tool is not configured. If you want to use a merge tool other than the default, git choose open diff in this case because the command was run on Mac OS. You can see all the supported tools listed at the top, one of the following tools. Just type in the name you'd rather use. Interesting. Hey Ferg, any tips to stay awake? Just hang out with me here. Use this stream as a way to keep yourself accountable. So if I'm reading here, then read on your own and just use it as a way to, like, we're hanging out in a study session together back in college. Right? If you're happy with, okay, so after you exit the merge tool, Git asks if the merge was successful. If it tells, if you tell the script that it was, it stages the file to mark it as resolved for you. You can run git status again to verify all the conflicts have been resolved. If you're happy with that and you verify that everything that had conflicts has been staged, you can type git commit to finalize the merge commit. The commit message by default looks something like this. If you think it would be helpful to others looking at the merge in the future, you can modify the commit message with details about how you resolve the merge and explain why you did the changes you made if these are not obvious. Okay. 3.3, Git branching, branch management. How many sections are there? Let's see. Okay, we're halfway. So it doesn't look that long. Branch management. Now that you've created, merged, and deleted some branches, let's look at some branch management tools that will come in handy when you begin using branches all the time. The git branch command does more than just create and delete branches. If you run it with no arguments, you get a simple list of your current branches. Now, notice the star character that prefixes the master branch. It indicates that the branch that you currently have checked out, i.e. the branch that the head points to. This means that if you commit at this point, the master branch will move forward with your new work. To see your latest commit on each branch, you can run git branch-v. So we'll say git branch just shows you all branches. By itself, when called, will show all branches. Then we have git branch-v, right? Shows the last commit on each branch. The useful -- merged and -- no merged options can filter the list of branches that you have or have not yet merged onto the branch you're currently working on. To see which branches are already merged into the branch you're working on, you can run git branch merged. So this will say shows what branches, shows which branches are already merged into the branch you're on. So on git branch merged on the master branch, issue 53 was merged into the master branch. Because you've already merged into issue 53 earlier, you can see it in your list. Branches on the list without the asterisk in front of them are generally fine to delete with the git branch-d. You've already incorporated their work into another branch, so you're not going to lose anything. To see all the branches that contain work that you haven't yet merged in, you can run git branch no merge. So this will show all branches that contain work you have merged in. Okay. This shows you other branch Oh, this shows your other branch because it contains work that isn't merged in yet. Trying to delete it with git branch D will fail. The merge testing is not fully merged. Are you sure you want to delete it? If you really want to delete the branch and lose that work, you can force it with the capital D. The options described above, merged and no merged, will, if not given a commit or branch name as an argument, show you what is respectively merged or not merged into your current branch. You can always provide an additional argument to ask the merged state with respect to some other branch. Okay. Do not rename branches that are still in use by other collaborators. Do not rename a branch like master slash main slash mainline without having read this section changing the master branch name. Suppose you have a branch that's called bad branch name and you want to change it to correct branch name while keeping all history. You also want to change that branch name on remote, GitHub, GitLab, or other server. How do you do this? Rename the branch locally with git branch-move command. Git branch-move bad branch correct branch. This replaces your bad branch name with correct branch name, but this change is only local for now. To let others see the corrected branch on the remote, push it. Set upstream. Now we'll take a brief look at where we are now. Notice that you're on the branch corrected branch name and it's available on the remote. However, the branch with the bad name is also still present there, but you can delete it by executing the following command: git push origin delete bad branch name. Now the bad branch name is fully replaced with the corrected branch name. Changing the master branch name. Changing the name of the branch like master, main, mainline, default will break the integration services, helper utilities, and build release scripts that your repository uses. Before you do this, make sure you consult with your collaborators. Also, make sure you do a thorough search through your repo and update any references to the old branch name in your code and scripts. Rename your local master branch into main with the following command: git branch move master to main. There's no local master branch anymore because it's now renamed to the main branch. To let others see the new main branch, you need to push it to the remote. This makes the renamed branch available on the remote. Now we end up in the following state. All of these here. And the head points to origin master. Your local master branch is gone. And it's replaced with the main branch. The main branch is present on the remote. However, the old master branch is still present on the remote. Other collaborators will continue to use the master branch as their base of their work until you make some further changes. Now you have a few more tasks in front of you to complete the transition. Any projects that depend on this one will need to update their code and or configuration, update any test runner configuration files, adjust build and release scripts, redirect settings on your repo to host for things like repo default branch, merge rules, and other things to match branch names, update references to the old branch in documentation, close or merge any pull requests that target the old branch. After you've done all of these tasks and are certain the main branch performs just as the master branch, you can delete the master branch. 3.4, git branching. Hey Andrew, how's it going? What do you want to learn, Andrew? Let me know more about you. What's your current situation? Thanks for joining me here. How you doing? All right, we got a couple more sections here, guys. Let's keep it going. Branching workflows. Now that you have some basics of branching and merging down, what you can or should do with them. In this section, we'll cover some common workflows workflows that this lightweight branching makes possible, so you can decide if you would like to incorporate them into your own development cycle. Long-running branches. Because Git uses a simple three-way merge, merging from one branch into another multiple times over a long period is generally easy to do. This means you can have several branches that are always open and that you use for different stages of your development cycle. You can merge regularly from some of them into others. Many Git developers have a workflow that embraces this approach, such as having only code that is entirely stable in their master branch, possibly only code that has ever been or will be released. They have another parallel branch named develop or next that they work from or use to test stability. It isn't necessarily always stable, but whenever it gets to a stable state, they can merge it into master. It's used to pull in topic branches. It is used to pull in topic branches, short-lived branches like your earlier issue 53 branch, when they're ready to make sure they pass all the tests and don't introduce bugs. In reality, we're talking about pointers moving from up the line of commits you're making. The stable branches are further down in your line of commit history, and the bleeding edge branches are further up in the history. So you branched off of developed topic. It's generally easy to think about them as work silos, where sets of commits graduate to more stable silo when they're fully tested. So you have the master branch, development branch merges into the master branch, and the topic merged this topic in development into the master branch. So the master branch always stays, and then as its original commit, and then you just merge into the master branch as you branch off from it to add more features. So you never actually commit on the master branch, you just continually merge into it. Andrew, what core and Bissell Phoenix, thanks for coming in. I appreciate you for joining me here. Welcome. My name is Michael. I appreciate you guys for being here. I'm a biochemist. I have a degree in human biology and a minor in chemistry, and I work as a formulation chemist for a 9-to-5 job. And I teach myself how to code afterwards. We've been going every day for the past almost like 6 months now, you guys. So thank you truly for being here and joining me every day. If you're here, consider leaving a thumbs up on the stream and subscribing. We just crossed over 1650. Woo! We're 50 subs away from 1700. We've been stuck in the 1600s for a while now, but that's okay. I started off with Harvard CS50P. It was a great introduction, and I highly, highly recommend you pair that book with Python Crash Course. I have read this book live on my stream just as we're reading GitHub now. It was the first book I ever read on stream, so the formatting is a little bit different. I was a little bit more of a noob stream back then. But I did read this live on stream, and I'm currently going back through and solving the try it yourself problems for you guys. I solved them independently on my own when I read it, but I'm solving them and posting solution videos to the Python Crash Course built in, or problems for you guys to also reference. So you guys can reference those videos currently on my channel. I also have a description or a Discord link down below, which is an entire roadmap for free for you guys to follow of my current learning journey so far documented on this stream. So every book I have in there organized for you pretty nicely to read and to get access to all of my notes on those books. Weekly course updates for the CS50 courses I've taken. We're currently working on our Harvard CS50X final project. We've watched all the lectures and completed all of the problem sets, and we're putting together our final project, which we're about 90% done with right now. So we've been working on that for the past few weeks too. So lots of stuff going on the channel. I really appreciate you guys being here. Little by little, we're chugging along and really moving. Okay, you can keep doing this for several levels of stability. Some larger projects also have a proposed or PU, proposed updates branch, that has integrated branches that may not be ready to go into the next or master branch. The idea is that your branches are at various levels of stability. When they reach a more stable level, they're merged into the branch above them. Again, having multiple long-running branches isn't necessary, but it's often helpful, especially when you're dealing with very large or complex projects. Topic branches, however, are useful in projects of any size. A topic branch, okay, let's say we'll say a proposed branch, or we'll say a topic branch, right? Topic branch is a short-lived branch. A short-lived branch that you create and use for a single particular feature or related work. This is something you've likely never done with the VSC before because it's generally too expensive to create and merge branches. But in Git, it's common to create, work on, merge, and delete branches several times a day. You saw this in the last section with the issue 53 and hotfix branches you created. You did a few commits on them and deleted them directly after merging them into your main branch. This technique allows you to context switch quickly and completely because your work is separated into silos or all the changes in the branch have to do with that topic. It's easy to see what has happened during code review such. You can keep the changes there for minutes, days, or months and merge them in when they're ready, regardless of the order in which they were created on or worked on. Consider an example of doing some work on master, branching off for an issue 91, working on it for a bit, branching off the second branch to try another way of handling the same issue 91 v2 is going back to your master branch and while working there for a while and then branching off to do some work that you're not sure is a good idea, dumb idea branch, your commit history will look something like this. Whereas you have the master branch, you're doing work on it. You have issue 91 branched off from here, which tries again from here. And then dumb idea is right here with you're on your master branch. Now let's say you decide that you want a second solution to issue your best issue 91 v2 and you showed the dumb idea branch to your coworkers and it turns out to be genius. You can throw away the issue 91 branch, losing commit C5 and C6 and merge the other two. Your history then looks like this, where dumb idea is associated with issue 15. It's merged to we created a new merge onto commit C14 of the which references a parent back to issue 91 v2. You merge those two branches together. We'll go into more detail about the various possible workflows for your Git project in distributed Git. So before you decide which branching scheme your project will use, be sure to read that chapter. It's important to remember that you're doing all of this that these branches are completely local. It's important to remember when you're doing all this that these branches are completely local. When you're branching and merging, everything is being done in your only in your Git repository. There is no communication with the server. What was the V? What was the V? I have a section in my Discord, Abyssal Phoenix, where you can get access to this as well as my repo for my notes if you want access to those too. It's called ProGit. Okay, 3.5. Last section, Git branching, remote branches. Yeah, we'll do a leave after this one, Mahan. We're almost done. All right, remote branches. Remote branches are references, pointers in your remote repositories, including branches, tags, and so on. You can get a full list of remote references explicitly with git ls remote. So this or this. Right. So what does this say? You can get a full list of remote references. Get a full list of remote references for remote branches as well as more information. Nevertheless, a more common way is to take advantage of remote tracking branches. Remote tracking branches are references to the state of remote branches. They're local references that you can't move. Git moves them for you whenever you do any network communication to make sure they accurately represent the state of the remote repository. Think of them as bookmarks to remind you where the branches in your remote repositories were the last time you connected to them. Remote tracking branches names take the form of remote/branch. For instance, if you want to see the master branch on your origin remote, looked like as of the last time you communicated with it, you would check the origin/master branch. If you were working on an issue with a partner and they pushed up an issue 53 branch, you might have your own local issue 53 branch, but the branch on that server would be represented by the remote tracking branch origin issue 53. This may be a bit confusing, so let's look at an example. Let's say you have a Git server on your network at git.ourcompany.com. If you clone from this, Git's clone command automatically names its origin for you, pulls down all its data, creates a pointer to where its master branch is, and names it origin/master locally. Git also gives your own local master branch starting at its same place as the origin master branch, so you have something to work from. Origin is not special. Just like the branch name master does not have any special meaning in Git, neither does origin. While master is the default name for a starting branch when you run git init, which is the only reason it's widely used, origin is the default name for remote when you run git clone. If you run git clone/o booyah instead, then you'll have booyah/master as your default remote branch. So git.ourcompany has this master branch. You git clone to this clone as git.project.git. And now it pulls onto your computer the master branch and then origin/master. If you do some work on the local master branch and in the meantime someone else pushes to git.ourcompany.com and updates its master branch, then your history moves forward differently. Also, as long as you stay out of contact with your origin server, your origin/master pointer doesn't move. So in this person, someone else pushes some code here, and I'm still on origin master on this snapshot. To synchronize your work with a given remote, you run git fetch remote command, in our case git fetch origin. This command looks up the server origin and looks up which server origin is, in this case git.ourcompany.com, fetches any data that you don't have, and updates your local database, moving your origin/master pointer to its new, more update position. To demonstrate having multiple remote servers and what remote branches for those remote projects look like, let's assume you have another internal Git server that is used only for development by one of your sprint teams. This server is at git.team1.ourcompany.com. You can add it as a new remote reference to the project you're currently working on by running git remote add command as we covered in Git basics. Name this remote team1, which will be your short name for that whole URL. So here's the origin, and here's team1. Now you can run git fetch team1 to fetch everything the remote team1 server has that you don't have yet. Because that server has a subset of data your origin server has right now, git fetches no data but sets a remote tracking branch called team1/master to point to the commit that team1 has as its master branch. So team1 has a master branch here, and now you pull down team1's basically point, okay, work here onto this commit frame. Pushing. When you want to share a branch with the world, you need to push it up to a remote to which you have write access. Your local branches aren't automatically synchronized to remotes to write to. You have to explicitly push your branches you want to share. That way you can use private branches for work you don't want to share and push up only the topic branches you want to collaborate on. If you have a branch named server fix that you want to work on with others, you can push it up the same way you push your first branch. Run git push remote branch. Push to origin that branch. This is a bit of a shortcut. Git automatically expands the serverfix branch name out to ref/head/serverfix colon or semicolon ref/head/serverfix, which means take my serverfix local branch and push it to update the remote's serverfix branch. We'll go over some of the ref heads part in details in git internals, but you can generally leave it off. You can also do git push origin serverfix colon serverfix, which does the same thing. It says take my serverfix and make it the remote serverfix. You can use this format to push a local branch into a remote branch that is named differently. If you didn't want to call serverfix on the remote, you could instead run git push origin serverfix colon awesome branch to push your local serverfix branch to the awesome branch on the remote project. Don't type your password every time. If you're using HTTPS URL to push over, the Git server will ask you for your username or password for authentication. By default, it will prompt you on the terminal for this information so the server can tell if you're allowed to push. If you don't type it every single time, if you don't want to type it you can set up a credential cache, the simplest way to keep it in memory for a few minutes, which you can easily set up by running git config global credential.helper cache. The next time one of our collaborators fetches from the server, they will get a reference to where the server's version of the serverfix is under the remote branch origin serverfix. Git fetch from origin, counting objects 7, compressing objects, remote total 3 unused, packing. Okay, it's important to note that when you do a fetch that brings down new remote tracking branches, you don't automatically have local editable copies of them. In other words, in this case, you don't have a new serverfix branch, you have only an origin/serverfix pointer that you can't modify. To merge this work into your current working branch, you can run git merge origin/serverfix if you want your own serverfix branch that you can work on. You can base it off your remote tracking branch. So you can check out and create that branch alone from origin serverfix. This gives you a local branch that you can work on that starts where origin serverfix is. Tracking branches, sorry. Thanks, Abyssal. Thanks for coming. It's in the description of this YouTube video, Abyssal. Hey AJ, welcome in, dude. Got a spammer on this Twitch here. Checking out of a local branch from a remote tracking branch automatically creates what is called a tracking branch, and the branch it tracks is called an upstream branch. Tracking branches are local branches that have a direct relationship to a remote branch. If you're on a tracking branch and type git pull, Git automatically knows which server to fetch from which branch to merge in. When you clone a repository, it generally automatically creates a master branch that tracks origin/master. However, you can set up other tracking branches if you wish. Wish some ones that track branches on other remotes or don't track the master branch. The simple case is you just saw. Oh my gosh. The simple case is the example you just saw, running git checkout -b branch remote / branch. This is a common enough operation that Git provides the -- track shorthand. Branch server fix setup. Okay. In fact, this is so common that there's even a shortcut for that shortcut. If the branch name you're trying to check out, A, doesn't exist, and B, it exactly matches a name on only one remote, Git will create a tracking branch for you. To set up a local branch with a different name than the remote branch, you can easily use the first version with a different local branch name. Server SF. Okay. Now your local SF will automatically pull from server fix. If you already have a local branch and want it set to a remote branch you just pulled down, or want to change the upstream branch you're tracking, you can use the -u or set upstream to option to Git branch to explicitly set it at any time. If you want to see what tracking branches you have set up, you can use the --v option to Git branch. This will list out your local branches with more information, including what each branch is tracking and if your local branch is ahead, behind, or both. So here we are. So here we can see that our issue 53 branch is tracking origin /issue 53 and is ahead by 2, meaning that we have 2 commits locally that are not pushed to the server. We can also see that our master branch is tracking origin /master and is up to date. Okay, so these trackings are just tracking from the server. Got you. Basically like pointers to that server index. It's important to note that these numbers are only since the last time you fetch from each server. This command does not reach out to the servers. It's telling you about what it has cached from these servers locally. If you want totally up-to-date ahead and behind numbers, you'll need to fetch from your remotes right before running this. You can do that like this. Git fetch all, git branch --v. Pulling. Awesome. Did you get in the Discord, Phoenix? Pulling. While the git fetch command will fetch all the changes on the server that you don't have yet, it will not modify your working directory at all. It will simply get the data for you and let you merge it yourself. However, there is a command called git pull, which is essentially a git fetch immediately followed by a git merge in most cases. If you have a tracking branch set up as demonstrated in the last section, either by explicitly setting it or having it created for you by the clone or checkout commands, git pull will look up what server and branch your current branch is tracking, fetch from that server, and then try to merge that remote branch. Deleting remote branches. Suppose you're done with a remote branch. Say you and your collaborators are finished with a feature and merged it into your remote's master branch, or whatever branch your stable code line is in. You can delete a remote branch by using the delete option to git push. If you want to delete your server fix branch from the server, you run the following. Basically, all this does is to remove the pointer from the server. The Git server will generally keep the data there for a while until a garbage collection runs, so if it was accidentally deleted, it's often easy to recover. Interesting. Oh, one more section. Rebasing. In Git, there are 2 main ways to integrate changes from one branch into the other, merge and the rebase. In this section, you'll learn about what rebasing and how to do it. The rebase tool. If you go back to an earlier example from basic merging, you can see that that you diverged from your work and made commits on 2 different branches. The easiest way to integrate the branches, as we covered before, is the merge command. It performs a 3-way merge between the 2 latest branch snapshots and the most recent common ancestor of the 2, creating a new snapshot and commit. However, there is another way you can take a You can take the patch of the change that was introduced in C4 and reapply it to the top of C3. In Git, this is called rebasing. With the rebase command, you can take all the changes that were committed on one branch and replay them on a different branch. For this example, you would check out the experiment branch and then rebase it onto the master branch as follows. This operation works by going down the common ancestor of the two branches, the one you're working on and the one you're rebasing onto, getting the diff introduced by each commit on the branch you're working on, saving those diffs to temporary files, resetting the current branch to the same commit as the branch you're rebasing onto, and finally applying each change in turn. What in the world? At this point, you can go back to master branch and do a fast forward merge. Now the snapshot pointed to by the C4 prime is exactly the same as the one that was pointed to by C5 in the merged example. There's no difference in the end product of the integration, but rebasing makes for a cleaner history. If you examine the log of rebase branch, it looks like a linear history. It appears that all the work happened in series, even when it originally happened in parallel. Often you'll do this to make sure your commits apply cleanly on a remote branch, perhaps in a project to which you are trying to contribute but you don't maintain. In this case, you'd do your work in a branch and then rebase your work onto origin/master when you are ready to submit your patches to the main project. That way, the maintainer doesn't have to do any integration work, just a fast forward or clean apply. Note that the snapshot pointed by the final commit and you end up with, whether it's, oh my god, I cannot read, so annoying. Note that the snapshot pointed to by the final commit you end up with, whether it's the last of the rebase commits for a rebase or the final merge commit for a merge, is the same snapshot. It's only the history that is different. Rebasing replays changes from one line of work onto another in the order they were introduced, whereas merging takes endpoints and merges them together. You can also have your rebase replay on something other than the rebase target branch. Take a history like a history with a topic branch off another branch, for example. You branch a topic branch server to add to some server-side functionality to your project and made a commit. So here, you branched off at C2 and committed here. Then you branched off that to make a client-side change called client and committed a few times. Finally, you went back to server branch and did a few more commits. Yeah. Suppose you decide that you want to merge your client-side changes into your machine for a release. You want to hold off on your server-side changes until it's tested further. You can take the changes on clients that aren't on server and replay them on your master branch by using the -- onto option of git rebase. This basically says take the git client branch, figure out the patches since it diverged from the server branch, and replay those patches in the client branch as if it were based directly off the master branch instead. It's a bit complex, but result is pretty cool. So then does it sync out through here? Now you can fast forward your master. Yeah, see fast forwarding up to that point. Because it included everything from C2. And then if you don't have any conflicts, you can just merge the master will fast forward up. Let's say you decide to pull in your server branch as well. You can rebase the server branch onto the master branch without having to check it out first by getting git rebase base branch topic branch, which checks out the topic branch in the server, in this case server for you, and replaces it onto the base branch master. This replays your server work on top of your master work as shown in rebasing your server branch on top of your master branch. So the server branch goes, got copied, pasted in, and then you move those forward and delete the branch. You can remove the client and server branches because all the work is integrated. You don't need them anymore. Boom. But the bliss of rebasing isn't without just drawbacks, which can be summed up in one line. Do not rebase commits that exist outside your repository and that people may have based on work on. If you follow that guideline, you'll be fine. Do not rebase commits that exist outside your repository and that people may have based work on. If you don't, people will hate you and you'll be scorned by friends and family. When you rebase stuff, you're abandoning existing commits and creating new ones that are similar but different. You push commits somewhere and others pull them down and base work on them. And then you rewrite these commits with git rebase and push them once up again. Your collaborators will have to remerge their work and things will get messy when you try to pull their work back into yours. Let's look at an example of how rebasing work that you've made public can cause problems. Suppose you clone from a central server and then do some work off that. Your commit history looks like this. C1 master from the server, you pull down C1, you branch off, and you do work on it. Now someone else does more work on that includes a merge and pushes that work to the central server. You fetch it and merge the new remote branch into your work, making your history look something like this. So you get all the information from the current and then pull down into here. Fetch more. Okay, next, the person who pushed the merge work decides to go back and rebase their work instead. They do a git push force to override the history of the server. Then you fetch from that server, bringing down the new commits. Now you're both in a pickle. If you do a git pull, you'll create a merge commit, which includes both lines of history, and your repository will look like this. I have no idea what's going on, to be honest, with this rebasing crap. If you run a git log, when your history looks like this, you'll see two commits that have the same author, date, and message, which will be confusing. Furthermore, if you push the history back up to the server, you'll introduce all those rebase commits to the central server, which can further confuse people. It's pretty safe to assume that other developers don't want C4 and C6 to be in the history. That's why they rebased in the first place. If you do find yourself in a situation like this, Git has some further magic that might help you out. If someone on your team force pushes changes that overwrite work that you've based work on, your challenge is to figure out what is yours and what they've written. It turns out that in addition to the commit sh1 checksum, Git also calculates a checksum that is based just on the patch introduced with the commit. This is called a patch ID. If you pull down work that was written and based on if you pull down work that was rewritten and rebased it on top of the new commits that from your partner, Git can often successfully figure out what is uniquely yours and apply them back on top of the new branch. For instance, if the previous scenario, if instead of doing a merge when we're at someone pushes rebase commits, abandoning commits you've based your work on, we run git rebase team1/master. Git will determine what work is unique to our branch, determine which are not merge commits, determine which have not been rewritten into the target branch, apply those commits on top of team1/master. So instead of the result we see in the you merge this, we would end up with something more like rebase on top of forced pushed rebase work. Is this chapter done yet? Jesus. This only works if C4 and C4 prime that your partner made are almost exactly the same patch. Otherwise, the rebase won't be able to tell that it's a duplicate and will add another C4-like pattern, which will probably fail to apply cleanly since the changes you've already would already be at least somewhat there. Dude, I cannot. I don't really understand this that much. Spartans, do you have a better explanation, Sparty? for rebase? I'm not really following this that well. You can simplify this by running a git pull dash dash rebase instead of a normal git pull, or you could do it manually with a git fetch followed by a git repaste team1 slash master in this case. If you are using git pull and want to make rebase the default, you can set the pull.rebase config value with something like git config global pull.rebase true. If you only ever rebase commits that have never left your own computer, you'll be just fine. If you rebase commits that have been pushed, but that no one else has been based commits from, you'll also be fine. If you rebase commits that have already been pushed publicly and people have based work on those commits, then you might be in for some frustrating trouble and the scorn of your teammates. If you or your partner does find it necessary at some point, make sure everyone knows to run git pull dash dash rebase to try to make the pain after it happens a little bit simpler. Rebase versus merge. It's a book, but I think it's in a docs form here or something like that. It's just a separate, different format, but it's a book, yeah. Now that you've seen rebasing and merge in action, you may be wondering which one is better. Before we can answer this, let's step back a bit and talk about what history means. One point of view on this is that your repository's commit history is a record of what actually happened. It's a historical document, valuable in its own right, and shouldn't be tampered with. From this angle, changing the commit history is almost blasphemous. You're lying about what actually transpired. So if there was a messy series of merge commits, that's how it actually happened. And the repository should preserve that for prosperity. The opposing point of view is that the commit history is the story of how your project was made. You wouldn't publish the first draft of a book, so why should you show your messy work? When you're working on a project, you may need a record of all your missteps and dead end paths. But when it's time to show your work to the world, you may want to tell a more coherent story of how to get from A to B. People in this camp like to use tools like Rebase and Filter Branch to rewrite their commits before they're merged into the mainline branch. They use tools like Rebase and Filter Branch to tell the story in the way that's best for future readers. Now, to the question of whether merging or rebasing is better, hopefully you'll see that it's not that simple. Git is a powerful tool that allows you to do many things and with your own history, but every team and every project is different. Now that you know how both of these things work, it's up to you to decide which one is better for your particular situation. You can get the best of both worlds, rebase local changes before pushing to clean up your work, but never rebase anything that you've pushed somewhere. Okay, so if you push stuff to a thing and you fetch it back down and then you rebase off of that, well, people might be working on your previously fetched work, so you rebased, and so it's completely changed. Yes, Barty, well, definitely. Do you know any resources where they have practice commands for solving certain problems in Git? Like, I'm sure that there's like online, games or something out there for um, if you kind of like on YouTube. Okay, well, maybe we'll have to watch that after we finish the book. We'll watch like a video and get some practice after we finish the book to put it into play. Thanks so much for being here, guys. We're at 16:53. You guys are awesome. My name's Michael. I have a degree in human biology and a minor in chemistry, and I work as a formulation chemist for a biotech company. I make biological controls, a lot of different biological solutions, blood, urine, serum, plasma, lots of different stuff. Um, and these controls are used for patient diagnostics and research, and I've been teaching myself how to code for about 10 months now. I started with Harvard CS50P and read Python Crash Course, and have been reading DSA in Python and Fluent Python, and we are currently over halfway through DSA in Python, and we're about a quarter of the way through on Fluent. And we are doing Pro Git here, so we got a lot of books going on right now. We're also working on our CS50X final project. So for those that don't know, we have a final project that we're working on, which is a full business manager into Kinter with Python. and it's really cool. I can show you guys that a little bit later. All right. That's it for 3.6. I'll have to go back through and get some better notes. I kind of was just trying to focus on what the content was saying, and I stopped kind of taking notes. So I'll go back through in my free time and do another pass and take some better notes for you guys, and then push that up. So let's just go ahead and git commit. We'll say finished. If you guys want access to these notes, they're on my GitHub for you guys. I have not used any of them, but I'm going to check on some of them right now. No worries. Sparty, you should join my Discord. Link down below for free. It's just roadmap, and we can hang out offline in there. All right, let's solve one leak code problem before I sign off for tonight. I will be back though tomorrow. I stream every single day around 7 p.m. PST. Okay, we're on binary tree post order traversal. So in this example, it gives you 4, 6, 7, 5, 2, 9, 8, 3 back to root. Okay. So for post order, well, for pre-order, what we did was, right, we have a results. We define a traverse function. If the node is none, we return off of that node. We append the value at every node we visit. We call left and right. So if the node is a okay. So let's call here a results list that we'll save our values in. Let's create a function called traverse. We'll take in a node, right? We're going to say so our base case would be if the node, so let's think about this in terms of just individual trees. So you want to go left as far as you can. If there is no more left value, and if you reach a leaf, you take that point on starting from the left. So you recursively call to the left. So we'll just have our base case here, and then we'll say if node, if not node dot left and not node dot right, meaning that it's a leaf, no, we don't want to append on a leaf, right? Because that'll only append the 4, 6, 7, and 9 values. We want to append the return of this value back up to the previous root value. So we'll just have a, so if there's a left node, we want to traverse the left. So we'll call left equals to node dot left. right? If left so left equals to traverse on node left. So we'll traverse on node left all the way down until we reach a base case where there is no more left. And there, so I guess their base case would be a leaf node. So if node is none, what do we want to return? We just want to return back up. So if we come here, call left, okay, it's none. We return back up to that node. So we are starting on the ones place. We need to move left as long as we can. Okay, we moved all the way down to the 4. We go one more. Okay, we realize that that's a none. We've gone too far. We return back to our 4. So this returns, if the node is none, return back. So this will call node.left recursively until we reach down until a node and return back. To the current node of 4. So can we go right equals to traverse node dot right, and we say if left if there is a left value if there is a left value and a right value, then we're going to let me look up on my DSA notes here. Or no, let's go to DSA in Python. And let's go to trees. Let's look here. Here we go. So post-order traversal. Binary trees in order. Breadth first, post-order traversal. For every child in the tree, do post-order traversal on it. Okay, so recursive solution is trivial. Could you do it iteratively? So if the node that we're currently on in the recursive call is none, we return back to the previous node, which would be this guy here, or this guy here, this guy here, this guy here, a leaf. Right? Which would be our base case. Right? As if you have a node that has no children. So return back. The left of this for node is none and the right is none. So what do we need to do? We need to append the for and return back. If there's a right, okay, so we'll say this. So if not left and not right, we're going to go results dot append node dot value, right? If it's a leaf, if you have a right, if not left and not right, you append the node value, right? You append the node value at that point in time. And then you just return back. No, if no. So elif, so if left, so if right, so if you have a left value, so let's go like this. Let's say if not node dot left and not node dot right, append and return. If node dot left and not node dot right, else we're going to call Hey Luis. No, this is trees. Trying to figure out post order traversal here. So we want to reach all the node here and then go back up to there. So in this case, we go 3, 2, 1. So if there's a left, go left recursively until you reach a root, append that root, or append that leaf, and go append, append, append. But if there's a right, you want to recursively do that one first, and then have that returning call. So if not node left and not node right, results append and return. That's our base case, right? So this returns back up to here. Let's think here. I am having a little trouble working through the logic of a post-order traversal. Don't show me any code or give it away. Let me get there using you. We want to visit all leaf nodes and append those to a results. This is all children nodes. All deepest. We want to visit all deepest children nodes first and append the values before returning back to root. Imagine you're standing at a node. What's the very first thing you would do in post order? Not code, just the very first general action. If I'm standing on a node, the first thing I would do, I would need to check if it has kids. So if node dot, so we'll go if not node dot left and not node dot right, we're going to return going to results dot append node dot val. Okay. We're going to deal with the left first. The left. You're standing on a node and you see a left child. You go left. Unless you're standing on that left child, same rules apply. So if node dot left, right, if node dot left, call return traverse node dot left. Append value and return. If node left, we're going to call traverse on node left. And return that value. Right? If node dot right, return traverse. If not any of them, if left, go left. If right, go right. This will only append. So you're standing at a node and you see a left child, you go left. Now you're standing on that child. The same rules continue. What do you do next? Go left. you reach a null node or a child or a leaf. Once you hit a node with no children, a leaf, that's your first chance to append its value. Now let me ask, after appending the value of that leaf, what's your next move? Return back to the previous recursion. Go right until leaf. Draw all the way down to the leaf, then append that value and bubble back up. So once you've handled all that, once you handle all that, you append the current node. You append the current node value, which is the subtree root. Dang it. No. Oh. So we got to call the function. So call traverse on root, and we'll return this. None type has no attribute left. There's no none. None type has no attribute. If you're on a child, you append the node value and return that returns back append results, and then you return at the end of this function none type has no attribute left if not node and not right. So it's getting to none. So if node left, call traverse left. If node right, call traverse right. Else append result value of that node and return. So can I get rid of this? Do like this? No, none type object has no attribute left. Oh, for what test case though? Is it saying for an empty node, like that's the start? Oh, so for a blank. Okay, so we'll say okay, so that passed that, but we're getting null back. So if I take this out, call traverse left, call traverse right. Still getting null. So if I call traverse left, call traverse right. Oh, there's no right, there's no left, there's no right. You append and return. So if there's no left, no right, you return the value. You call this. So this one wouldn't work either. No, still getting null back. So if not node dot left and not node dot right, then we append the value because we're on a leaf and return back to the previous recursion. We then say if node left, so my pre-order, I'll return return results. Very end. None type has no attribute left. So call on root. Return results. So if it's none, yeah, the debugger is for pro model, the pro version. I'll sometimes throw them into my personal IDE and debug if it doesn't have these like nodes though. They have these custom objects, so it makes it kind of difficult. But some of them I'll do it on my own. Okay, so if node, we're gonna say if node, if root, we'll call this, and we'll return results. Boom. Okay, got it. I think we got it. Yeah! Woo! Yes! Leave a thumbs up for that one, boys. 175 is done. All right. So I wonder if we can go like this. Traverse left. Return. Will this pass? No. It's saying no dot left, if no dot left. Sweet. Alright, let's see how it likes this though. Okay. I solved it. Here is my answer. That passed the checks. Let's go. That's clean and nicely thought through. You nailed the logic. The way you handle the leaf checks up front is cool too. Post order doesn't need a single out leaf like that, but it works, totally works to make sure. Yeah, right, because we're already doing an append on a leaf down here, if not, right? So this will still work, I think. Yeah. Yeah. Okay, so I'll give it this. Okay, I get it because a leaf would fail the first two ifs and auto append and return at the end of the pass. Exactly, you're on the right track. If you hit a leaf, it'll skip the left and right checks and go straight to the append and then return. No extra calls needed for a leaf. Woohoo! Got that one. Mr. Mahan, you there? We did it. I don't know. Are you there, Mahan? Mahan. All right. Leave a thumbs up for that one, boys. All right. Let's see here. I'll probably be done, but I'll just look at this one here. Intersection of two linked lists. Given the heads of two singly linked lists, return the node at which the two lists intersect. If the two linked lists have no intersection at all, return null. Huh. It intersects on 8. Okay. 2 skips on A versus 3 skips on B. Okay, I get it. So we'd have to move forward. So values can duplicate though. So it's not like we can check on the values. Given the heads of two singly linked lists, return the node at which the two lists intersect. It's not like you can move at the same time either because you might miss it. Because the lists are different lengths with different positions of where they might intersect. Huh. So if you move on once on A and move once on B, and move once on A and move once on B, well, you're already at C for A, but you're still on B3. Oh, I know how to just solve this one. So what we need to do, oh, we're given heads though. Oh, right. Could we not determine the length, right? And then traverse sooner, one ahead. Right? If we ever get to a point where, right, where node A point, in this case here, B3 is going to point to a a head of B will point to head of A. So if at any point as you move one step further, oh, okay, so let's do this. So while head A dot next does not equal head B dot next or head B dot next does not equal to head A dot next, right? We're going to continually say now what if they move at the same time? So while call next, so can we, well, if these two lists are always of, in every example they gave, the lists are of differing lengths, right? So can we not just move a value forward, a value forward? Well, if we move a value forward here and a value forward here, so that won't work actually. So because in this case, if we move a value forward and move a value forward, well, if we're kind of trying to say, well, eventually this node will point to a B node because they're going to intersect. And if they never do, then they never do. Like on here, you move forward one, you move forward one, you move forward one, you move forward one. Well, now your B node is pointing to an A node, so you have a crossover. But in this case, you move forward one, and you miss your intersection by going over one. So that approach is not correct. Hey, Brian. So if you move one forward, if you're on this node, how do you check its intersection? If they're both pointing to the same node itself, well, what if there happens to be another 8 node here? Huh. All right, you guys, I'm going to think about this one. We solved the post-order traversal one today, and we finished Git chapter 3. Come on. What the heck? Yeah, we saw binary tree post-order today. All right, you guys. Thank you so much for joining me here. We will jump back into Pro Git Chapter 4 tomorrow. Thank you guys so much for being here. This one looks like it might be a little long. Oh boy. Oh, that one's short. That one's short. That one's short. That's short. That's also short. That's short. That's short. That's short. That's short. Okay, so chapter 4 is really short. Nice. Sweet. Yeah, Brian, I have a full-time job as a formulation chemist. I have a degree in human biology and a minor in chemistry. And I work a 9 to 5, and I teach myself afterwards. So these are long days, guys. These are long days, let me tell you. It's starting to take its toll on me little by little. My sleep schedule is starting to catch up on me. I can feel myself, it's getting slower and less, energy for getting the stuff done. I've got to switch things up and get back on track. All right, you guys. I'll see you guys tomorrow at the normal time around 7 p.m. PST. Thanks for joining me again. Truly, you guys, it has been awesome hanging out with you. We'll come back tomorrow and read chapter 4 of Pro Git. If you guys want access to the resources, please join the Discord link down below where you can get access to all of my study resources, including this most recent Pro Git book and notes. I have weekly updates for our Harvard CS50X course that we're currently working on, and we're building the final project for, which is our small business manager project in Python using Tkinter as our GUI element. It's a really, really great project that takes in inventory expenses. You can transact and return inventory items, and then it'll automatically create income statements and balance sheets according to those data points. So it's really, really cool from there. Does the back end double entry accounting like we want, which is really awesome. So thank you guys truly for being here with me. I will work on the project tomorrow after we finish Pro Git chapter 4, and we'll hopefully get that project moving on and almost finished. So thank you guys so much for being here. See you guys. Thanks so much for being here.